Hey folks, in this video we're going to talk about gravitational potential energy. Now up until now, the topics that we've discussed are ones you pretty much would have done last year in AP Phys 1. So today we start a topic that you would not have talked about in AP Phys 1, and that's gravitational potential energy. Now you may be saying to yourself, well wait a minute Mashar, I got this covered. Isn't gravitational potential energy MGH? And the answer is sure, if your changes in height are small. Okay. So, if your things are rolling down a hill or a car is moving around or a roller coaster is moving around, MGH is just fine. But what if you have significant changes of height? For instance, what if you go from the surface of the Earth to the height of the International Space Station, 211 miles up off the ground on average? Well, then you can't use MGH because G changes with altitude. As a matter of fact, in the previous video, we calculated G up there is about 8.8. So you'd be off by at least some percent of potential energy. And the higher the altitude, the farther you get from Earth, the farther off you'd be in your calculation of potential energy. So what is a proper equation that will work every time, no pun intended, to find changes in potential energy if you're talking about significant distances? Well, now we have to use calculus. All right, so this is something that you would not have done last year. So let's say you got the Earth. So here's the Earth, and you're going to want to draw this picture kind of big. Now remember, we're measuring everything from the center of the Earth, and that's important. Well, let's say you go from location A here to location B here. Okay, that's a significant change in height, and G is going to change significantly there. And I'm going to draw a line that goes from the center of the Earth through those 2 points and keeps going. Okay, and here's what we're going to do. We're going to find the change in potential energy from A to B. Okay, so we're going to go from A to B. Now, will that be a positive or negative change in potential energy? Well, you all should know it's a positive change in potential energy. You're gaining altitude, you're gaining height. If I drop something from A and it hits the ground, if I drop something from B, it's going to be going faster when it hits the ground. So clearly it's a positive change in potential energy. So it's important to know that because we're going to be doing a lot of sign changes here in the next few moments. So there you go. All right, so we know that change in potential energy is negative work done by a conservative force. Okay, a reminder about that. So for instance, let's say you're doing a simple problem where you're dropping a book on the floor. As the book falls, gravity's doing positive work on it, but the book and the Earth are losing potential energy. So that's the easy example to think about. And the equation for work is the integral. Now, because I got a negative here, I got to put that same negative there, okay, of force dot dr. And in this case, it's going to be a dr because we're talking about different radii, okay? Now, so I'm going to use this and this, okay? So delta U is negative the integral. What's our force? Well, our force is negative G, mass of one object, mass of the other. Now, in this case, let's say this is a book. So the two masses here would be the Earth and the book, okay? Over r squared, that's in the r hat direction. So remember, the negative is a direction. Well, we need that here, dot dr. Okay, in other words, when we're moving to the right, that's our dr, okay, that's our little dr. The force is to the left. The force is pulling back toward Earth. So that's where this negative is coming from there, okay? Well, and then our limits, we're going from r sub a to r sub b. Okay, so that's our limits. And as we've discussed in class, every time we do an integral in here, we're going to have limits. We're going to do definite integrals every time. All right, so how many negatives we got in this whole thing? Well, we got 2. So they're going to cancel out, okay? So you got delta U from A to B, which we know should be a positive answer. Now I'm going to pull out everything that's a constant here. G, mass 1, and mass 2 are all constants. And what am I actually integrating? Okay, I'm actually integrating dr over r squared from RA to RB. Okay, so this will become G m1 m2. What's the integral of r to the negative 2? So if I said what's the integral of r to the negative 2 dr, You add 1 to the exponent and then divide by that new exponent, right? So that's what we're going to have here. We're going to have negative 1 over r. R to the negative 1 is 1 over r. We're going to evaluate this from RA to RB, all right? And so if you do that, you get G mass of 1, mass of 2, okay, times negative 1 over RB minus negative 1 over RA. And if I tie that up, delta U from A to B is G, mass of one object times mass of the other, times, and then I'll put it this way, 1 over RA minus 1 over RB. Now, first of all, we know it should be positive. Is it? Okay. Well, A is smaller than B, if you look back at the picture. Okay. So 1 over A is bigger than 1 over B. So this is a positive value. So this is a positive answer. Okay. Now, this is the actual equation you use to find changes in potential energy. Now, there's something else to think about. Previously, when we used MGH, the choice of 0 potential energy was arbitrary. So let's say you were dropping a book from a countertop to a floor. You could call 0 the countertop, or you could call 0 the floor. Well, in this equation, it turns out that there is actually a set 0 that you have to use as 0. Okay, there is a 0 potential energy. Where is that? Okay, well, if, okay, you make R infinity, what's 1 over infinity? Well, that approaches 0. So it turns out if R sub A approaches infinity, okay, then the potential energy at A approaches 0. Okay, so like let's say you started way out here somewhere at infinity, okay, you would have 0 potential energy there. And then you let the book go. So the book's going to go flying toward B, right? Well, as the book goes flying toward B, it should lose potential energy. Well, wait a minute, if it starts with 0 potential energy, how can it lose potential energy? Well, it turns out that potential energy is always negative. So it starts off at 0 at infinity, and as you fall toward the Earth, let's say, the potential energy becomes more and more negative, okay? So there's actually an equation for the potential energy as a function of R is equal to, well, if you say A is infinity, this becomes 0, you have a negative out front, so you get negative G, mass of 1, mass of 2 over R. So that is the equation for potential energy at any point. So if I have 2 objects, here they are, this equation tells me how much potential energy they have together. And again, it is always negative. If you push them infinitely far apart, it becomes 0. If they get any closer, it becomes negative. Okay. Now, I'll end with one more mathy thing, and in the next video, we'll do some actual numerical examples. But here's the other mathy thing that I'll end with. Okay. Remember what an integral is. It's an area. Okay. So let's say you were to graph force of gravity, okay, versus R. Okay. And let's say this is the radius of the planet. Okay, so we're going to start there. Well, the force is negative, right? And the force would look something like this. It would never be 0, but it would approach 0. And remember, our force of gravity is negative G m1 m2 over r squared. Okay, so if I were to graph that, it would look like this. Now, by the way, later on, we'll talk about what if you start drilling into the planet. Don't worry about that for now. So it turns out that this equation that we just came up with here is a way of finding this area. So let's say you want to know how much energy it takes to go from this radius to infinity. Okay. Well, technically, this area goes to infinity. This line or this curve never technically touches the r-axis here. Okay. So technically, this area goes off to infinity. But that area has a finite value. That area is equal to this. Okay, so it's kind of an interesting math thing where you can find the finite area of an area that has an infinite dimension to it. So think about that when you're talking about calculus. But it turns out that this area, again, even though it goes off to infinity, it has a finite value to it, and this number is that finite value. Okay. So again, in the next video, we'll do some actual numerical examples. We'll get out your calculators, and we'll start talking about what I call orbital mechanics. So I hope this video was helpful, and thank you very much.